All right, this is grade 6, unit 2, lesson 6. And in this lesson, students are going to be continuing to talk about that equivalent ratio stuff, but this time we're going to be introducing the double number line diagram. It's kind of a new thing. So parents and teachers, this is probably not something you were taught back in the day. But we are going to be teaching it to our students now as we march towards all this sort of standard algorithm stuff that we're more familiar with. But right now, that double line diagram is really a useful tool for helping students kind of understand about equivalent ratios and how to use that understanding of equivalent ratios to eventually solve some proportions. So let's get started. All right, we're going to start with our number talk, and it's the same, similar one. We've done this similar to in previous lessons. Basically, the idea is let's use a problem as a jumping point so that we could do future problems, right? So 4.5 times 4. So if we're going to be thinking about that, that's going to be kind of like our home problem. So we're going to think about that 4.5 as 4.5. And so if we're going to think about 4 times 4.5, that's really 4 times 4 plus it's 4 times a half, which is really 16 plus 2, which is 18. So the idea is we can think of this as 18. There's other ways we could have done it. We could have said, let's see, this one. All right, so I'm going to erase all this. And we could have said, hang on, I'm getting there. So we could have said like 4.5 times 4. We could have done the doubling halving technique. We could double this to get 9 and halve this to get 2. And then all of a sudden we get 18 as well. So there's a variety of ways we could have gotten that answer. But then the point is, for this next problem, we're supposed to know that the first factor stayed the same, but the second factor doubled. Well, since the second factor doubled, that tells us that the product is going to double. So instead of 18 as our answer, we're going to get 36. And then in a similar kind of fashion, we see that these next two kind of go together, that the 65, that factor stays the same, but the 1/10 suddenly doubles and becomes 2/10. So if we think about what is 65 times 1/10, and we kind of just know our place value that is 6.5. 1/10 of 65. If we're going to divide 65 by 10, we know that the digits go to the one space to the right, or you could think of it as the decimal goes one space to the left, and then you get 6.5, and then therefore this one is going to be twice as much because 2/10 is twice as much as 1/10, and so our final product is going to be 13. All right, we're going to introduce this new thing called a double number line. And the double number line is really actually kind of a cool thing right here. It's a great way for us to understand ratios and equivalent ratios. So the other day we made drink mixtures by mixing 4 teaspoons of powdered drink mix for every 1 cup of water. So here's a way to represent that, right? In one batch right here, as indicated by this kind of circly thing, you got a ratio of 4:1. But if you have a second batch, now suddenly you have another 4:1, so a total of 8:2, right? Now, here is a way to represent that. So we have right here our ratio of 4:1. 4 drink mix to 1 cup of water. All right, 8 teaspoons of drink mix for 2 cups of water. And we see that right here visually, and then this is how a little bit more abstract on that number line. So we can see that if we continue, that if we wanted to, we could say, so if we had 5 cups of water, then we would have another 4 cups or teaspoons of drink mix, so that would go to 20, from 16 to 20. So that's the idea. And heck, if we wanted to, we could have 6 cups of water and 24 cups or teaspoons of drink mix. or 7 cups of water and 28 teaspoons of drink mix, and we could just go forever and ever and ever. So the question right here is, how can we tell that 4-to-1 and 12-to-3 are equivalent ratios? How can we tell that 4-to-1 right here and 12-to-3 are equivalent ratios? Well, one, they both show up on the same number, double number line. But another way for us to think of it is, here's our 4-to-1, here's our 12-to-3. I'm going to zoom in a little bit. Whoa! I'm going to zoom in a little bit. All right. Whoa! I don't want that. Okay, and so the idea would be, and I want to group these. Where is it? Oh, group. Come on, baby. I want to group. Okay, anyway. So the idea, stinker butt. Okay, there we go. All right, so if we want to make sure that 4-to-1 and 12-to-3 are equivalent ratios, well, we can take a look and we can see that, oh, look at that. 4 times 3 gives us 12, and 1 times 3 gives us 3. Therefore, these two ratios are equivalent, right? So that's one way to be thinking about it. Is that the only way to explain it? Absolutely not. There are other ways. So how are these representations the same, and how are they different? I guess what they're asking is, is the picture representation different from the double number line? And so the picture's a picture, the number line is a little bit more abstract, isn't it? But they are the same in that they both show equivalent ratios that we can see. A ratio of 4-to-1 is the same thing as 8-to-2, and we can see that right here in the double number line, that they both show a collection of equivalent ratios, but they are different in that the picture's a picture and the number line is a little bit more abstract. So let's keep going. So how many teaspoons of drink mix should be used with 3 cups of water? That's this question right here. And so in order to answer that, we're going to have to go, and if we have 3 cups of water right here, oops, nope, that's 2 cups of water. Right here, 3 cups of water means we're going to need 12 teaspoons of drink mix right there, because that's the idea. And if you look at the picture, that really kind of makes sense, because if we had just added 1 more cup of water, we would have needed 4 more teaspoons of drink mix, and then we would have had 3 cups of water and 12 teaspoons of drink mix. So there is our answer right there. So I'm going to scroll down, and so our answer is 3 cups of water would require 12 teaspoons of mix. All right, and then number 4, how many cups of water should be used with 16 teaspoons of drink mix? So that's kind of, we're just going to the opposite direction, really. So now if we have 16 teaspoons of mix, how much water will we need? There it is. We will need 4 cups of water. So we would need 4, and let's do it in blue, 4 cups of water, good old H2O. And then lastly, what numbers should go in the empty boxes on the double number line diagram? Well, I actually answered that already earlier today in this slide, so we're all good. So here we've got another double number line story here. We've got a diagram showing Elena's recipe for light blue paint. And it looks like we need 2 cups of white and 6 tablespoons of blue, but we can also see a smaller, the same ratio using smaller numbers, that we have 1 cup of white paint for 3 tablespoons of blue paint. And we're supposed to create a double number line. Now, it doesn't matter whether we put the white paint on top or the blue paint on the bottom, or reverse it, as long as we're consistent for this entire problem. But at this point, I'm going to put the white on top, the blue on the bottom, just to keep consistent with our picture up here. And we see a couple of ratios, don't we? We see that there's a ratio of 1 cup of white to 3 tablespoons of blue. So I'm going to do that. I'm going to do 1 and 3 right here. And then I see that we have, collectively, we have 2 cups of white is 6 tablespoons of blue. So there is our 2 and 6. And I'm already starting to see a pattern. If we had a third one here, we would have 3 more and tablespoons, so that's 3 and 9. So I can start to see a pattern that every time the white goes up by 1, the blue goes up by 3, and we could just keep going right there. Number 2, compare your double number line with your partner. Right there. And so really, there's not a lot of choices you had. I mean, you could have swapped the white and the blue, in which case the multiples of 3 would be on the top, and these whole numbers, just the 1, 2, 3, 4, 5, would be on the bottom. But that's about it, really. I guess you could have considered each of these to be a half, each line interval, so the one, you know, but there's not a lot of choices here. Moving on to number 3. How many cups of white paint should Elena mix with 12 tablespoons of blue? So we see our 12 tablespoons of blue, and since that's our 12 tablespoons of blue, and we can look straight up, that means we need 4 cups of white paint. Question number 4. How many tablespoons of blue should Elena mix with 6 cups of white paint? So if we're going to scroll up here, and I didn't actually write it down, so let's write it down, because we need 6 cups of white paint, which means we're going to add 3 for the blue, and we're going to have 18. So if we have 6 cups of white, that means we're going to need 18 tablespoons of blue. And so let's write that down. 18 tablespoons. All right. Number 5. Use your double number line to find another amount of white paint in blue that could make that same shade. So basically, they're just asking, what's another ratio? Well, if we wanted to, we could say, okay, let's make this 7, 8, 9. Let's go up to 9. So that means this is going to be 21, this is going to be 24, and this is going to be 27. So there's another ratio we could have included. Heck, we could have chosen 8 and 24. We could have chosen 7 to 21. We could have chosen any of those, and that would all work. And how do you know that these mixtures would make the same shade? Well, because we're following the pattern, aren't we? As long as we follow the pattern for our double number line, that means we are good. But if you really want to, I don't know, give another more mathematical answer, we could choose, starting with this first ratio right here, we could choose any ratio, ratio. Let's do 6 and 18. And we know that they're going to have a common multiplier. For example, 1 times 6 gives us 6, which means 3 times 6 gives us 18. And since there's that common multiplier for the white row and the blue row, in this case it's 6, that tells us that these two ratios are equivalent. So our summary for this lesson is really talking about that idea that a double number line, you start with your given ratio and you're creating equivalent ratios simply by following a pattern. In this case, if I add 5, I'm going to add 2. If I add 5, I'm going to add another 2. If I add another 5, I'm going to add another 2, etc. But we can then also choose any two ratios that we're claiming are equivalent, and then we can find that common multiplier. So in this case, the common multiplier, I don't know, 5 times 4 gives me 20, so therefore 2 times 4 gives me 8. And since this ratio jumping to this ratio have that common multiplier, that means these two ratios are equivalent. So let's do our practice problems for lesson 6, and we're going to begin with a particular shade of orange paint. And it has 2 cups of yellow for every 3 cups of red. So there's our ratio, 2 to 3. All right, 2 cups of yellow for every 3 cups of red. On the double number line, you see that they have made a double number line for us. Circle the numbers of cups of yellow and red needed for 3 batches. Ooh, so if we want 3 batches of orange paint right here, well, let's see, right here. This is 1 batch. This makes 2 batches. Therefore, this makes 3 batches right there. So 3 batches is right here. Interestingly enough, this means if you have 0 batches, you're making 0 batches, 1 batch, 2 batch, 3 batch, that means this must be 0 batches, because in order to make 0 batches of paint, you need no yellow and you need no red. So that makes sense. That's actually kind of cool. All right, so as we keep going, this double number line shows the amount of flour and eggs needed for 1 batch of cookies. Right here, there's 1 batch of cookies. Complete the diagram to show how much is needed for 2, 3, and 4 batches. So let's fill it in. So another 5 cups of flour would require another 3 eggs. Another 5 cups of flour would require another group of 3 eggs. And lastly, another 5 cups of flour is going to require another 3 eggs. So there is our completed double number line. Of course, we could keep going forever, so you're never really finished filling out that double number line. And then question B, what is the ratio of cups of flour to eggs? So what is the ratio of cups of flour to eggs? Well, any one of these ratios would work. I'm going to use the simplest one, which is 5 to 3. So the ratio is 5 to 3. How much flour and how many eggs are used to make 4 batches of cookies? Right? Well, here's 1 batch. Here's 2. Here's 3. Here's 4. There it is. Our 4 batches of cookies. Is it cookies? Yeah. Is we would need 20 cups of flour and 12 eggs. 20 to 12. How much flour is used to with 6 eggs? Well, here's our 6 eggs, so we would need 10 cups of flour. 10 cups of flour. And then lastly, how many eggs are used with 15 cups of flour? Well, here's our 15 cups of flour, so we would need 9 eggs. We would need 9 eggs. All right. Number 3. And then B, and there's an A up there, and then a B and a C down here. All right, so here is a representation showing the amount of red and blue paint needed. And ultimately, they're telling us this is making 2 batches of purple paint. Well, if this is making 2 batches of purple paint, that means just this one circle-ish oval thing is going to make 1 batch, right? So we need to, on a double number line, label the tick marks to represent things, right? So let's go down, because there is our double number line right here. So the ratio is 3 to 2. All right, so we have 3 reds for 2 blues, another 3 reds, so that's 6. Gives us another 2 blues, so that's 4. Another 3 reds is 9, so that's 2 more blues. And then lastly, another 3 reds, that gives us 12, requires another 2 blues. So there is our 8 for the blue. All right, so there is part A. Now part B says how many batches will be made with 12 cups of red. So that's 1 batch, 2 batches, 3 batches, 4 batches. So that's the 4th batch with 12 reds and 8 blues. So how many batches are required for 12 reds? That's 4 batches. 4 batches. And then number C, how many batches are made with 6 cups of blue? So there's 2, 4, 6. There's my 2, 4, 6 right here. And I can see that that's 1 batch, 2 batches, 3 batches. So we can make 3 batches with that 6 cups of blue. Number 4, Diego estimates that there will be 3 pizzas for every 7 kids. Select all that is true. So the ratio of kids to pizzas is 7-3, and that is absolutely true. The ratio of pizzas to kids is 3-7. 3 pizzas, 7 kids, so that is also true. Let's see. The ratio of kids to pizzas is 3-7. 7 kids, 3 pizzas. So kids to pizzas is not 3-7. It's actually 7-3. So that is false. All right, I'm going to squeeze this in here. The ratio of pizzas to kids is 7-3. Pizzas to kids is not 7-3. It's actually 3-7. So that is false. And then E, for every 7 kids, there needs to be 3 pizzas. For every 7 kids, there needs to be 3 pizzas. Yeah, that's a true statement. That is a true statement. So there we go. We had 3 trues. We had 2 falses. All right, and then number 5, draw a parallelogram that is not a rectangle that has an area of 24 square units. All right, so we know that a parallelogram, the formula for the area of a parallelogram is base times height, right? So we know that let's see, go away. The area of a parallelogram is base times height, and we want the area to be 24, which means we can have a base of 8 and a height of 3. All right, but they want it to not be a rectangle. Well, that's cool. So we're just going to, I'm going to zoom in a little bit. I know I need to have a base of 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's my base of 8 right here. Now they want a height, we need a height of 3. Remember, we need a height of 3 because I just decided what times what would give me 24, and I chose 8 times 3. I could have chosen 6 times 4, but I chose 8. So I need to have a height of 3. All right, so I'm going to zoom in a little bit here. I need to have a height of 3. Now, a height of 3, 1, 2, 3. Here's my height of 3, but I need to offset it, because if I just do it right on top, right here, that's going to make me a rectangle. And they said no rectangles. So great, I will offset it by a little bit, and I'll say 1, 2, 3, 4, 5, 6, 7, 8. There is my parallelogram that has an area of 24. It's got a base of 8. It's got a height of 3. Therefore, I know it's got an area of 12 square units. All right, so draw a triangle that has an area of 12 square units. Oh my goodness. Explain how or show how you know the area is 24 square units. So the area of a triangle, remember, the area of a triangle is, let's get here you go. Area of a triangle is base times height divided by 2. All right, so I need something that's going to be 48 divided by 2. So I need 2 numbers that are going to multiply to give me 48. So I know I could do 6 times 8, which means my base is going to be 6, my height is going to be 8. So when I draw that triangle on my, oh, there it is, right here. So I need to have that triangle have a base of 6 and a height of 8. All right, so let's base of 6. So 1, 2, 3, 4, 5, 6. There's my base of 6. I needed to have a height of 8. So I need to count. And I'm going to zoom in a little bit, so this is going to help us. So I needed to have a height of 8. So 1, 2, 3, 4, 5, 6, 7, 8. So my height has to be up there. A height of 8. There's my height of 8. Boom. I could have chosen a height of 8 right here. I could have made that my triangle, either the blue one or the yellow one, because in both cases I know that our base is 6, and in both cases I know that the height is 8. In this case, the height kind of is right here. In this case, the height is outside of the triangle itself, right? So they all have a height of 8. And so I gave you 2 triangles to choose from, the blue one and the yellow one. And I think that's all the practice problems. And that wraps up grade 6, unit 2, lesson 6. Students were using that double number line to understand equivalent ratios.